Section 1. Introduction. So far I've been able to get away without being too precise about the properties of the rings we're working with. I said back in video 3 that our rings are called Dedekind domains, but I chose to avoid giving the full definition of that term too early on in the course. However, if we're not careful in choosing the right ring, problems can arise. Let's take Z adjoin root 5 as an example. Here's a picture of Z adjoin root 5 as a lattice, and here's the ideal generated by 2 inside it. Now remember that the norm of an ideal is a sort of area or volume scale factor. If you stretch this fundamental cell for the ring on the left to become a fundamental cell for the ideal on the right, you've had to stretch by a factor of 2 horizontally and 2 vertically, so 4 in total. The norm of the ideal 2 is 4. Now, 2 is not a prime ideal in this ring. In fact, there's exactly one ideal of norm 2 which contains it, the non-principal ideal generated by 2 and 1 plus root 5. I'll call this ideal P. Here's a fundamental cell for that ideal. Its norm is 2. So we'd expect to be able to factorize 2 as a product of prime ideals as P squared. But what happens when we calculate P squared? Well, I'll write it out. 2 times 2 is 4. I'll mark that point on my diagram in the bottom left. 2 times 1 plus root 5 is 2 plus 2 root 5, which is here on the diagram. This is also 2 plus 2 root 5. And 1 plus root 5 times 1 plus root 5 is 6 plus 2 root 5, which is here on the diagram. Okay, let's fill in the lattice they span. And it's not too hard to check that this is an ideal of Z adjoin root 5. But here's where we see that things have gone wrong. Firstly, here's what the ideal 2 looked like. These two clearly aren't equal, so P squared is not equal to 2, and as P squared was our only candidate for a prime factorization of 2, 2 must not have a prime factorization at all. This also has all kinds of knock-on effects. For example, the norm of P squared is actually 8, so the norm is no longer multiplicative. In fact, you can check that 2 times P is actually equal to P squared, so if what I told you about ideal classes is true, we should be able to invert P. The class of the ideal 2 in the ideal class group should be equal to the class of P. But the class on the left contains only principal ideals, and the class on the right contains only non-principal ideals. So what's gone wrong? Well, the problem is that Z adjoin root 5 isn't a Dedekind domain. Section 2. Dedekind domains. In the example of Z adjoin root 5, we saw an example of 2 ideals of norm 2 whose product has norm 8. Now, norms are meant to be multiplicative, and 2 times 2 is not equal to 8. But norms are volume scale factors. In other words, volumes relative to the lattice formed by the ambient ring. Perhaps we're dealing with the wrong ring. Notice that if, hypothetically, we had some ring R containing Z adjoin root 5, and R had twice as many points, it seems as though all of these norms would double. So presuming this equation of ideals still makes sense in R somehow, we'd have 2 ideals of norm 4 whose product has norm 16. So we would have fixed this multiplicativity problem. But can we find a ring R like this? And have we caused any other problems? We're finally at a stage where we need the rather complicated definition of Dedekind domains that I didn't want to give earlier. I'll state it in algebraic language, and I'll try to explain roughly what each of the terms means. Here's the definition. A ring R that is not a field is called a Dedekind domain if it is an integrally closed, Noetherian domain of Kroll dimension 1. This is a very jargon-dense definition, so let me try to explain all of these terms individually, including a couple we've seen before. I'll start off by reminding you that a ring is something like Z, or Z adjoin I, or Z adjoin the cube root of 5. It has arithmetic operations, addition, subtraction, and multiplication. And I'll remind you that in this course we're most concerned with the ideals in a ring, which we should think of as a kind of generalization of numbers. In particular, when the ideal I is contained in the ideal J, we want to be able to interpret this to mean the number represented by I is divisible by the number represented by j. A field is a special kind of ring, like Q or Q adjoin omega or C. These all have addition, subtraction and multiplication, but they also have the special property that you can divide by anything in the ring other than 0. So for example, Z isn't a field because you can't divide by 2 in Z. The number 1 divided by 2 no longer exists in Z. Unfortunately, fields themselves are arithmetically very boring. Anything other than 0 is a unit, nothing is prime, and there are no non-trivial ideals whatsoever, which is why we're not interested in fields. I won't explain integral closure in this section, I'll come back to this later. Noetherian is a kind of finiteness condition. It tells you that you can't have an infinite chain of ideals, each one properly contained within the next. Remember that this means in the language of numbers that you can't have an infinite chain of numbers, each one properly divisible by the next. So if I start with a positive integer, I choose a non-trivial factor, then I choose a non-trivial factor of that, and I choose a non-trivial factor of that, and so on. Eventually this process has to terminate because I've hit a number that doesn't have any non-trivial factors. Those are our primes. A domain is a ring in which if A times B equals 0, then either A is 0 or B is 0. This is always going to be true when we're working inside the complex numbers. But it's also true working in Z mod pz, that is, the integers but with arithmetic taken modulo p, when p is a prime number. A ring is a domain if it sits inside a field. So a counterexample is Z mod 6Z, for example. 2 and 3 are non-zero mod 6, but 2 times 3 is 0 mod 6. So Z mod 6Z is not a domain, and it can't be embedded inside any field. To explain Kroll dimension 1, I'm going to start by pretending the 0 ideal doesn't exist. And with this caveat, Kroll dimension 1 means the following. If P and Q are two prime ideals with P contained in Q, then P must actually be equal to Q. So again, in the language of positive integers, we can't have two distinct prime numbers, P and Q, such that P is divisible by Q. This sounds like something we obviously want if ideals are going to mimic arithmetic, but due to some technicalities in the definition of the term prime ideal, this doesn't come for free, and we need to assume it. In practice, for the sorts of rings we've been working with so far, all of these 5 properties are very easy to check. Z adjoin root 5 satisfies all of them. But I've left the trickiest property for last, integral closure. We'll explore this in the next section, but before I explain it, let me make one remark. If we can tick off all 6 of these properties, including the integral closure property, so that our ring is a Dedekind domain, then we do get all of the nice properties we'd hoped for. All non-zero ideals factor uniquely into prime ideals, ideal classes form a group, and this interpretation of ideal containment as divisibility that I've written in the top left can be made true in a literal sense, and so on. Section 3. Algebraic integers. An algebraic number, which you might know as the opposite of a transcendental number, is a complex number alpha satisfying an equation of the following form. Cn alpha to the n plus Cn minus 1 alpha to the n minus 1 plus ... plus C1 alpha plus C0 equals 0, where all of the Ci are rational numbers. In fact, by multiplying through by the denominators, we might as well assume right from the beginning that they're integers. And to make sure this equation is non-trivial, I'm going to insist that the top coefficient is non-zero. This criterion is equivalent to saying that if you start with the rational numbers q and you adjoin alpha, the field you end up with is finite dimensional as a Q vector space. So we call this a finite extension of Q. But in order to do what we've been doing, we need to ask the following question. Q adjoin alpha is an extension field of Q, and Q contains this special subring Z with the nice multiplicative theory. So what's the right analogue of Z inside Q adjoin alpha? What's the right ring to put in this corner here? Something that acts like the integers, but in some broader context of algebraic numbers. Well, to discuss that, we need to define algebraic integers. An algebraic integer is a complex number, alpha, satisfying an equation exactly as before, except this time Cn equals 1. The polynomial is monic. So I'm just going to go ahead and set Cn equal to 1. This important condition is what makes our rings look like discrete lattices. So let me call the set of algebraic integers A. This is actually a large subring of C. And let's go back to the question above. What ring do we choose to fill in the final corner of that square? Let's suppose K is a finite extension field of Q, and we've got some ring O, a finite extension ring of Z, and a lattice, some potential candidate for that final corner. In this context, we say that O is integrally closed in K if it's equal to K intersect A. That is, O is integrally closed if it contains all of the algebraic integers in K. So O is the maximal lattice, which is also a ring, inside K. Here are some examples. The set of all algebraic integers in Q, that is, Q intersect A, is just Z. This is the usual thing we mean when we say the ring of integers, though sometimes I've called elements of Z rational integers to make sure there's no ambiguity at this stage. The set of algebraic integers in Q adjoin I, that is, Q adjoin I intersect A, is just Z adjoin I, the ring of Gaussian integers. Notice that I is an algebraic integer because it satisfies x squared plus 1 equals 0, and that polynomial x squared plus 1 is monic. The set of algebraic integers in Q adjoin omega, where omega is that cube root of unity we've mentioned a few times now, is Z adjoin omega, the ring of Eisenstein integers. And again, omega is an algebraic integer because it satisfies x cubed minus 1, which is monic. By the way, these equalities aren't all obvious. It's normally easy to show that everything in the rings on the right is an algebraic integer, but it can be harder to show that every algebraic integer is contained in these rings on the right. We'll see some tricks for proving that later. So now, what's the set of all algebraic integers in Q adjoin root 5? Well, while this definitely contains Z adjoin root 5, because root 5 satisfies a monic polynomial equation, x squared minus 5 equals 0, so it is an algebraic integer, this set isn't equal to Z adjoin root 5. We'll come back to how to find missing elements in a future video, but for now let me just give the answer away. There's an element 1 plus root 5 all over 2, which isn't in our lattice Z adjoin root 5, but it is an algebraic integer. In fact, if we expand our lattice to include this element, we get the ring Z adjoin 1 plus root 5 over 2, which turns out to be the full ring of integers of Q adjoin root 5. We now have enough background to state the following fact. If K is a finite extension field of Q, then the set of its algebraic integers is a ring, and it's a particularly nice ring. In fact, it's always a Dedekind domain. So everything we've done over this video series applies to the ring of algebraic integers of K. At the start of the video, we outlined a problem that arose when we tried to do arithmetic inside Z adjoin root 5. I'll leave you to check that inside the larger ring Z adjoin 1 plus root 5 over 2, that problem no longer occurs. Finally, just a bit of terminology. This ring of all algebraic integers inside K, sometimes called O subscript K for clarity, is called the ring of integers of K, so I'll use that term going forward. Let's change tack briefly. Here's a basic but important fact about algebraic integers and monic polynomials. Given some algebraic number, say alpha is 1 plus I root 3 over 2, or beta is 2 minus the cube root of 5 over 3, how can we tell whether it's an algebraic integer or not? Well, it's easy to rearrange these expressions until we get some monic polynomial equation satisfied by alpha or beta respectively, in which all coefficients are rational. So for example, on the left, I might start off by multiplying both sides by 2, and subtract 1 from both sides, square both sides, and now I'll rearrange this to get all the terms on the left. And finally, I'll divide out by this top coefficient. So we have a monic polynomial in which all coefficients are rational, satisfied by alpha. On the right, I might multiply by 3, subtract 2, cube both sides, rearrange again, and divide out by that top coefficient. These polynomials are called the minimal polynomials of alpha and beta. They're not just monic polynomials that alpha and beta satisfy, they're actually the monic polynomials of smallest degree that alpha and beta satisfy. Now, algebraic integers satisfy monic polynomials with integer coefficients. For example, the minimal polynomial for alpha has integer coefficients, so alpha is an algebraic integer by definition. But what about beta? Its minimal polynomial doesn't have integer coefficients, but could beta potentially satisfy some other larger degree monic polynomial that does? In fact, the answer to this is no. To check whether an algebraic number is an algebraic integer or not, you don't have to check all possible polynomials it might satisfy. It's enough just to check its minimal polynomial. I might say a little bit more about this in the future, but I'll leave it here as an unproven fact for this video. Section 4. Discriminants. Suppose I've got some finite extension k of Q, of degree n, and some ring O' sitting inside it, forming a lattice of rank n. How can I tell whether O' is the full ring of integers, OK, or not? Well, the fact that O' is a lattice tells us already that it's contained in OK, so the question is whether OK is bigger than O' or not. Let me start off by reminding you that k can be embedded into the complex numbers in a bunch of different ways. Let me call those embeddings sigma 1 up to sigma n, and let B be the set x1 up to xn, some basis for k as a vector space over Q. The discriminant of this basis is defined as the square of the determinant of the following matrix. The first column is all the embeddings of x1 in order, the second column is all the embeddings of x2, and so on up to the final column, all of the embeddings of xn. Now, this object looks quite mysterious, so let's tidy it up a bit. Firstly, let sigma be the map from k into c to the n that just combines all of these sigma i's into a single map. You may remember something very similar from videos 6 and 7, which we called the canonical embedding. I'm going to think of it as a column vector. Then this first column is just sigma of x1, the second is sigma of x2, all the way up to sigma of xn. Okay, so to make this picture easier to draw, I'm just going to draw the case when n equals 2. If our basis x1, x2 looks like this, and this is the unit square inside that basis, let's see what happens when we hit it with sigma. Sigma will send x1 somewhere, it will send x2 somewhere, and it will deform that unit square linearly, so its area will change by some scale factor. The discriminant is just the square of this scale factor. Notice that in our earlier context, when we were dealing with lattices, this was just a fundamental cell for the lattice. In other words, the discriminant is just another notion of volume of a fundamental cell. But this time it doesn't depend on choosing the right ambient ring, it only depends on the lattice formed by the basis B. And while I've only drawn it in 2D, this works in arbitrary dimensions if you replace the area of this parallelogram with some appropriate notion of volume of a fundamental parallelotope. So here's an example. Suppose that k equals q adjoin root 2. So there are two embeddings. Sigma 1 sends 1 to 1, and root 2 to plus root 2. And sigma 2 sends 1 to 1, and root 2 to minus root 2. In fact, let's take 1 and root 2 as our basis as well. Then its discriminant is the square of the determinant of a matrix, where the first column of the matrix is everywhere that 1 gets sent to, and the second column is everywhere that root 2 gets sent to. So 1 gets sent to 1 and 1, and root 2 gets sent to plus root 2 and minus root 2. Okay, this determinant is minus 2 root 2. You may remember that that was our volume scale factor in video 7 up to a sign, and so the discriminant is 8. I might say more on discriminants some other time. For now though, why is this useful? Well, because of the following two facts. Let's go back to our setup, where k is an extension of q of finite degree, O' is a lattice inside k of maximal rank, so O' contains some of the algebraic integers in k, and we get this nice little square of inclusions. But notice that O' might not contain all the algebraic integers, OK might be bigger than O prime? Well, firstly, under this setup, the discriminant of O prime, that is, pick any lattice basis for O prime and then take the discriminant of that basis, is an integer. Secondly, let's suppose the index of O prime in the full ring of integers OK is D. That is, OK has D times as many lattice points as O prime. Then the discriminant of OK is always the discriminant of O prime divided by D squared. And of course that's an integer too. So remember that OK is the maximal lattice. We want to find the maximal lattice, so the lattice with most points, so the lattice with the smallest fundamental cell. This is the same thing as minimizing the discriminant. So for example, if the discriminant of O prime happens to be square free, in other words, the only possible D squared we could divide by on the right is 1 squared, then O prime must equal OK. So let's apply this to when k equals q root 5. Let's first look at the lattice we started with, z adjoin root 5. Here's a picture of it. And a basis for it is given by 1 root 5. It has two embeddings, sigma 1 and sigma 2. They both send 1 to 1, but they send root 5 to plus and minus root 5 respectively. So now let's apply them both to our basis elements, first to 1, then to root 5. And let's take the determinant of the resulting matrix, which turns out to be minus 2 root 5. Then to get the discriminant, we square it, so the discriminant is 20. Now, the only squares that 20 is divisible by are 1 squared and 2 squared. So either the full ring of integers has discriminant 20, in which case it's this ring, z adjoin root 5, or it has discriminant 20 divided by 2 squared, so 5, in which case z adjoin root 5 is a subring of index 2 inside it. So OK has twice as many points as z adjoin root 5. Let's cheat again. Since we happen to know the answer in this case, what would have happened if we'd started with the right ring z adjoin 1 plus root 5 over 2? Well, here's a picture of z adjoin root 5, and here are the extra points we need to add to make it z adjoin 1 plus root 5 over 2. You can see we've multiplied the number of points by 2, so we're expecting the discriminants to differ by a factor of 2 squared. So here's a basis for this ring, 1 and 1 plus root 5 over 2. It has the same two embeddings, sigma 1 and sigma 2. So we're going to calculate the discriminant, and this time it comes out to be 5. Okay. 5 is square free. There are no more squares of integers that we could divide out by. That means our discriminant can't get any smaller. In other words, our lattice can't get any bigger. So z adjoin 1 plus root 5 over 2 is the maximal lattice, and therefore must be the full ring of integers O subscript q root 5. Now, we need the discriminant of OK to be minimal. It doesn't have to be square free. If the discriminant of O prime isn't square free, not all hope is lost. Let's see another example. Starting inside q adjoin root 3, let's look at the lattice z adjoin root 3. So here's a diagram, and here's a basis, 1 and root 3. Again, both our embeddings send 1 to 1, and they send root 3 to plus and minus root 3 respectively. Our discriminant this time comes out to be 12. Now, 12 isn't square free. 12 is divisible by 1 squared and 2 squared, so there are two possibilities. The discriminant of the ring of integers is either 12, in which case the ring is z adjoin root 3 and there are no bigger lattices of algebraic integers to be found, or it's 12 divided by 2 squared, so 3, in which case there is some bigger lattice of algebraic integers, and z adjoin root 3 has index 2 inside it. Let's suppose, and we'll find a contradiction in a minute, that the ring of integers has twice as many lattice points as z adjoin root 3. So, using our geometric intuition about lattices, there are only 3 possibilities for how to double the number of points while keeping the lattice structure. Here are the possibilities. It must look like this, or this, or this. More precisely, this first lattice is generated by a half and root 3. the second is generated by 1 and root 3 over 2, and the third is generated by 1 and 1 plus root 3 over 2. These lattices do all have discriminant 3 as lattices, but they'll all turn out not to work. Even though they're lattices, not all of their elements are algebraic integers. I recommend you pause the video now and try calculating the minimal polynomials of these 3 algebraic numbers I've labelled in blue, and concluding from there that they can't be algebraic integers. Alternatively, even though these 3 are lattices, they're not rings. Remember that rings have multiplication. So if I take any 2 elements of this lattice, if this lattice is a ring, and I multiply them together, their product must also be in the ring. So for example, in this first case, if this lattice forms a ring, then since it contains the number a half, it will have to contain a half times a half, which is a quarter, which is down here on the diagram. Our lattice doesn't contain that point a quarter. So we had to use our intuition to work out which possible lattices there were. For convenience later, here's a slightly more formal version of that argument. Pick an element of Q adjoin root 3, say alpha is b plus c root 3, where b and c are rational. And let's suppose it's in OK, but not in z adjoin root 3. Let's rearrange as before to find the minimal polynomial of alpha. If I subtract b, square, expand and subtract 3c squared, then I get this monic polynomial, alpha squared minus 2b times alpha plus b squared minus 3c squared equals 0. Now, since we're assuming alpha is an algebraic integer, this monic polynomial must have integer coefficients. So 2b must be an integer, and b squared minus 3c squared must be an integer. In the next section, we'll prove that this means that b and c are both integers, and so alpha was in z adjoin root 3 after all. The proof isn't too tricky, so you might want to pause the video at this point and attempt it yourself. In the next section, I'll spend a little bit of time going through it in detail, because it'll be a helpful introduction to a tool that we'll use later on. Section 5. Padic valuations. Fix a prime number p. I'm going to define a function v subscript p, called the padic valuation function, from the rational numbers to the integers union an extra element that I'll call infinity. Informally speaking, this function counts the number of times that a rational number is divisible by p. So let's suppose that the rational number x is p to the n times k over l, where k and l are both integers and p is co-prime to them both. Then vp of x is just that exponent n. So for example, v3 of 25 over 12 asks how many times the number 25 over 12 is divisible by 3. Let's factorise the top and the bottom of this fraction into prime factors. So 5 squared over 2 squared times 3. Now let's pull out the factor of 3 from the bottom, so it's 3 to the minus 1 times 5 squared over 2 squared. So the three-adic valuation of this is just this power minus 1. As another example, v7 of 98 asks how many times 98 is divisible by 7. Well, 98 is just 7 squared times 2, or 7 squared times 2 over 1 if you like. So the answer is 2. Finally, v11 of 6 over 7, well this is 2 times 3 divided by 7, which doesn't have any 11s in it at all, so 11 to the 0 times 2 times 3 over 7. So the 11-adic valuation of 6 over 7 equals 0. There's a special edge case here as well. The number 0 can be divided by any prime p as many times as you like, so we usually write that vp of 0 equals infinity. That's what that symbol infinity is doing in there. Here are some important facts for our purposes. Firstly, vp of a times b equals vp of a plus vp of b. And likewise, vp of a divided by b is vp of a minus vp of b. Here's a quick sketch proof. If the valuation of a is m, and the valuation of b is n, so we can write A equals p to the m times k over l, and b equals p to the n times r over s, where p is coprime to k, l, r, and s. Then multiplying them together, we get a times b equals p to the n plus n times kr over ls. And p must still be coprime to both kr and ls. Otherwise we get a contradiction from Euclid's lemma. Okay, so the valuation of ab is m plus n. Secondly, vp of a plus or minus b is at least the minimum of vp of a and vp of b. Okay, here's a sketch proof. Write a and b as above, and let's suppose that m is less than or equal to n. Then we can add a and b by finding a common denominator, and factorize out p to the m. Now because m is less than or equal to n, the number on the top here is still an integer, and p is still coprime to the number on the bottom, again by Euclid's lemma. We need to show that this is divisible by p at least m times, but there are m factors of p out the front, and maybe even some extra factors of p in the numerator, and none in the denominator. Same method works for a minus b as well. Thirdly, if vp of a is strictly less than vp of b, then vp of a plus or minus b is the minimum value vp of a. I'll let you prove that, it's very similar to the above. And finally, the integers are precisely the numbers with non-negative p-valuation for all primes p. That is, they're the rational numbers that, when put in simplest form, don't have any factors of any primes in their denominators. If you've never seen p-valuations before, you might like to take a minute to convince yourself of these facts. Earlier, we had two rational numbers b and c, such that 2b is an integer, say m, and b squared minus 3c squared is an integer, say n. Now, these p-adic valuation functions are a little overkill in this context, but we're going to use them as a way of carefully comparing prime factors to prove the following claim, that b and c must both be integers too. I'll be using the facts we just proved throughout this argument. So here's our proof. Let's deal with the prime p equals 2 first. Equation 1 tells us that b is half of an integer, so it's either still an integer, or it's some odd number divided by 2. Either way, it has at most one factor of 2 on its denominator, so the 2-adic valuation of b is at least minus 1. Now let's write c squared as the rational number b squared minus n over 3. What's its 2-adic valuation? Well, it's v2 of b squared minus n minus v2 of 3, but v2 of 3 is 0. So v2 of c squared is at least the minimum of v2 of b squared and v2 of n. Since n is an integer, v2 of n is at least 0, but v2 of b squared could be as low as minus 2. So this comes out to at least minus 2, and so, you can prove by contradiction, v2 of c must be at least minus 1. So c also has at most one factor of 2 in its denominator. Okay, what about primes other than 2? Well, since 2b is an integer, vp of 2b must be at least 0. But this is vp of 2 plus vp of b, and vp of 2 is 0 when p isn't 2, so vp of b is at least 0. And since c squared equals b squared minus n over 3, we can calculate vp of c squared. As before, that's just vp of b squared minus n minus vp of 3, which is at least the minimum of vp of b squared and vp of n minus vp of 3. This is at least 0, this is at least 0, and this is either 0 if p is greater than 3, or 1 if p is equal to 3. So in total, vp of c squared is at least minus 1, and so vp of c is at least minus a half. But p-adic valuations are integers, so vp of c is at least 0. In total, we've shown that the denominator of c contains at most one factor of 2, and no powers of any other primes. In other words, c is also half of an integer. We want to show that actually b and c are both integers. So let's rule out the other cases. These are the three cases that we drew earlier as lattices. If one of them is an integer, say b, and the other is an integer plus a half, say c, then let's look at this number b squared minus 3c squared again. The 3c squared term has two factors of 2 in the denominator. So it has two valuation -2. And the b squared term is an integer, so it has two valuation at least 0. So in total, the two valuation of the whole of the left-hand side must be the minimum of these, that's -2. But b squared minus 3c squared is supposed to be an integer, so its two valuation should be at least 0. This can't happen, this must be a contradiction. Of course, the same is true in the case where b is an integer plus a half and c is an integer. And so the final case we have left is when they're both an integer plus a half. Say b equals k plus a half and c equals l plus a half. We've done all we can do with these p-valuations, so let's just deal with this case directly. When I substitute these expressions in, b squared minus 3c squared turns out to be k squared plus k minus 3l squared minus 3l minus a half. But this isn't an integer either, so we can rule this case out too. At this stage you might like to pause the video and ask yourself why this proof shows that z adjoin root 3 has minimal possible discriminant, but why the same method of proof wouldn't show that z adjoin root 5 had minimal discriminant. What is it that explains the difference in their behaviour? And which behaviour would you expect for z adjoin root 17, and why? The final section of this video contains a big hint. Section 6. Rings of integers in quadratic fields. Finally, I'm just going to finish by summarising what we know about the quadratic extensions of Q in full generality. So, if k equals q adjoin root d, where d is some square-free integer, one of the following two things can happen. If d is 1 mod 4, then the ring of integers is z adjoin 1 plus root d over 2. This element has minimal polynomial x squared minus x plus d minus 1 over 4, and this is allowed because when d equals 1 mod 4, this number is an integer. And the discriminant of this lattice is d. On the other hand, if d equals 2 or 3 mod 4, then the ring of integers is z adjoin root d. This element has minimal polynomial x squared minus d, and the discriminant is 4d. So finally, we now know the right rings to work in to get unique factorization into prime ideals for all quadratic extensions of Q.